I'm sure ATOS will also have some problems too, but they have become less and less because of advances in treatments and advances in technology. For example, like Centrex. Centrex will eliminate a lot of problems, and so will Oculite. So if you look at this patient, what is the basic problem with this patient? I think Dr. Tran, earlier, a very attractive lady doctor, was talking to you about coma. And this is basically a patient who had plex done. And then it was done on the wrong type of eye. When you have certain types of eyes, you cannot treat with certain types of treatment. And I will go through and show you. Now, once this has happened, it's hard to recover. Patients become very, very conscious about their vision. They do this the whole day. And they come and sit down in front of you and they complain. Some of them come and cry. So, it's tough. So we all have to have a way to cure these problems. And most of them will tell you, doctor, I let you do it one more time. One more time. And I always tell the patients, I can't tell you that. I may need 2, I may need 3. And recently I did a patient for the 4th time, okay? And she is real tough, but I think I'm getting, with foresight, I'm finally curing her. So the thing is that I'm sure if you've done enough surgery, you will have this kind of problems. Now, this is another case they were sent to me. Can I perform LASIK? Can I perform PRK? Can I perform SMILE? So if you look at this, you look at that now, and this is quarter diopter scale, not 1 diopter, quarter diopter. Always look at your scans with quarter diopter scale. Okay, so you can see that something's fishy at the bottom there. So could be keratoconus, but nowadays we have better machines. Now if you look here now, on the left is MS39, both sides actually. And if you look carefully, you can see here it is, that's the anterior elevation. But look at what's abnormal. It's the epithelium over here. Everything else is okay. In fact, the epithelium is a little bit thin here and a lot thicker here. A lot thicker here over where it is. But look at the posterior curvature. Nothing abnormal in the posterior curvature. And then over here, again, the posterior elevation. More on the nasal side than anything else. Next slide for me. Sorry, more on the temporal side. Next slide. Oh, sorry. I have to do the next slide. Okay, here. There we are. So if you look here, you can see here, tangential anterior curvature, posterior tangential, nothing great, epithelial thickness. There you are. This is covered by the letters, but you can see it's very thick over here, very thin on top. So probably this patient has got a very tight lid, or she's been wearing contact lenses, and we used to call this contact lens distortion, because those days we can't look at the epithelium. So if you want to be a refractive surgeon, you have to spend the money, unfortunately, and buy this equipment like the MS39, OptoView, or all these machines can read epithelium, and they can read it very far out. That means you're reading it at way out there, which is 7-8 millimeters diameter. So you know what's going on over the whole cornea. So, okay, I can treat the eye. It's just epithelium. So which type of treatment would I do? I'll probably do a trans-PRK. And I'll explain to you why later. Now, let's say a person says, I want to do SMILE. I'm very good at SMILE. And it'll be great. The problem with SMILE and all lenticular extractions is that you're going to get the same thickness here as here. That means the top thickness of the lenticule is the same as the bottom thickness lenticule. Now, if you take out all of it being equal, what will happen is that this area is thicker overall. You got thicker epithelium, overall thickness is great. So when you finish the case, you you will get this kind of eye. Why? Because you didn't treat this area. With trans-PRK, you get rid of the epithelium as well. But you're not touching the epithelium, so you're going to end up with a lump of epithelium here. And therefore, it looks like you did a bad job. It's actually you didn't do a bad job. You chose the wrong treatment for the patient. So now we are getting more and more for sophisticated. We have CLEX, we have LASIK, we have SMILE. You have to choose which one. It's just like I want to do SICS. I want to do phaco. I want to do extra cap. I want to put in a glued IOL. I want to put in a scleral fixated IOL. So cataract, why? We have so many ways of doing cataract surgery. Why don't we have the same number of ways of doing refractive surgery? You cannot use one knife to cut all kinds of things. One knife to cut bread, one knife to cut fruits, one knife to cut vegetables, one knife to cut sushi. Everything will come out a mess. So you need a different knife for a different type of food. So why don't we have a different type of treatment for a different type of corneal problem or refractive surgery? So how do we know what to use? So well, we've got different tools now. If this is for people who use the Amaris, if you look here, they've added an extra button over here, and it's called Foresight. I wanted them to call it Smart Foresight, but I think it's been stolen by something else, so they can't use it, so they call it Foresight. Foresight means if you do a treatment, what are you going to get at the end of the treatment before you do the treatment? Mainly because if you do the treatment, it's actually going to be bad for the patient, and the patient's going to scream at you. I came with good vision, now I ended up with worse vision. So these are all for cases that are going to be borderline. You're not sure which way to go. What are you going to treat the patient with? So if you can predict what's going to happen, that's the best. That means anything you're not sure, funny looking cornea, not really ectasia, something irregular going on, and I'll show you a bunch of cases in a while. And then you end up with a situation where you can say to the patient, with the new technology, I can treat you and you come up with a good result. Sometimes a great result, because I've always warned the patients with abnormal corneas, your corneas may not behave the same as others. Okay? So, what is Shrink Foresight? Shrink Foresight is a sophisticated software with virtual post-operative corneal simulations. It creates a virtual replica of the patient's cornea based on treatment planning data and simulates the post-operative corneal shape by subtracting the ablation profile. So whatever shape you choose, whatever customization you do, you can know what the cornea looks like after that. Now, all of you are experts. This afternoon, I was watching everybody's slides. You know what an abnormal cornea looks like, and you know what a good cornea looks like. I remember many years ago when we didn't have all these sophisticated tools. One lady came in. Before she came in, I saw the topography. The topography was beautifully round, one big circle in the center, well-centered, beautiful color, large transition zone, everything. She came in and kissed me on the cheek. And I remember that topography for the rest of my life because I know that basically this is a really good eye. Now you buy a Nikon camera, you look at the gentleman taking photos of me now. If you look at his lens is round. His lens is round, it goes from the center to the curvature, it has an aspheric surface. That's why he pays so much money for the lens. And what do you think the cornea should look like? The cornea should look like an aspheric lens. So if you produce a beautiful round central right over the visual axis and a nice transition zone, the patient's going to come in and give you a kiss as well. Okay? So, allows the surgeon to dry run the surgery and visualize outcomes pre-operatively. Okay? Now, okay, so here comes this patient now. He's got an old scar here. And people say, why do you have a scar that's flatter and scar? Because the scar destroyed some of his corneal tissue here. and then his epithelium tried to heal as much as possible, but couldn't complete it. So he has a groove over here. He comes to me and says, can you do something? So you can say, okay, I do ICL. But if you do ICL, are you going to cure this problem? You're not. He's still going to have higher order aberrations. He's still going to have coma from here, and he's going to have just distortion and even scattering of light there. So what do? Well, if you look at this patient now, you see his cornea is not that thick, 496, 520. And if you look here, see this here? This is in red. This tells you that his corneal epithelium is thicker than normal, but yet he's flat. So what does that mean? His cornea thickened as much as it can, but it still cannot go to normal curvature. So he's got a groove. He's got a groove over here, which is not great for vision. Okay. This is his wavefront. You can see he's got a big patch over here. Even in normal pupil size, he cannot be corrected to full 6.6. And that's because he has coma. And then you can see, look at his scar thickness is 187. His epithelium increased up to about 90, but still cannot fill the gap enough. So these are the type of patients come to me, and look at his vision, it's still pretty good. So here we are. That's his summary page of his eye. So here we are. We give his treatment. Now we go through, we do the calculation, and we put in foresight. Now you input what data? You input the tomographic data. So you can only do this with the Cirrus, and you can only do it with the MS-39. You cannot do this with just the anterior surface topography. It is both anterior and posterior surface. You're taking into consideration both surfaces before you do your simulation. Okay? It calculates and visualizes the post-operative corneal shape. Is intuitive graphical interface resembling the diagnostic devices. That means it looks like not what you expect. No additional effort for surgeon, enhances pre-operative planning and patient education. You show the patient, this is what I'm going to do for you. This is what I should get. Okay? Flow chart of data input to simulation output. This is my wish. Later I'll show you how I'm trying to get straight to make it even easier for everyone. That means do multiple simulations at the same time. So you get all the simulations at one go instead of doing it one by one by one by one. Some cases I do 50 simulations because all the toughest cases come to me. Here we are. So here you've got here, over here, this is pre-operatively, and you see post-operatively definitely better, but not perfect. But look at the nice round circle over here. You got rid of that. Okay, you've got two types of scale. You've got the set scale, which I asked Srin, why do you make your own? And you've got the MS-39 scale. I tend to use the MS-39 scale nowadays more and more. They give you the predicted, let me see whether, here. They give you a lot of things. They give you the pre-operative refraction. They give you the post-operative refraction. Now, you get plus 0.18, and then you get a bit of cylinder, minus 0.55 at 99. This is 165, this is 99. So I flipped the astigmatism. What does that mean? It means I overcorrected the astigmatism. What does that mean? It means the optometrist who's measuring the patient, including me, we give too much cylinder because we don't have a coma lens. If we have a lens we can put in the trial frame with coma, put it in, but they don't make such a lens. Theoretically, it can be done. Okay, so I ended up putting in too much coma, too much cylinder, because that's what the refractionists put in. That's what I put in. But there's no coma lens. And coma is very similar to cylinder in visual matters. So by putting in the cylinder, the patient says, I see clearer. But actually it's coma, it's not cylinder. Okay? So we cut it down. So now we know, okay, too much cylinder. We now reduce the cylinder. Okay? And then you can see the final coma, the final trefoil, the final spherical aberration, the final trefoil, and the final higher order aberration. And you can compare this to this. You see the total RMS is 0.1 something over here and 0.06 after that. So you can tell the patient, I'm going to get rid of a lot of your higher order aberrations. Not everything, but a lot. I mean, one day maybe we'll be able to make everything 0, 0, 0, 0 here. Okay? Nowadays, some of my auto refractions come back all zeros. And that's the most satisfying thing. Okay. I can't go through every feature, sorry. I can't go through every feature, but there are many, many features. You can change a lot of things. And then it can give you the simulations of what you do. Even changing the optical zone. Recently, I had a patient who has a hyperopia after refractive surgery. She came to me, and then when I did the simulation, I ended up with a double ring. Do you know why I ended up with a double ring? Your optical zone of your hyperopia doesn't match the myopia zone of the myopia. So you end up steep, flat, steep, flat. And then do you think the patient will be happy? That's like people wearing those diffractive IOLs, you know, you end up with a lot of halo and glare. So you have to slowly adjust your optical zone. And I have a whole bunch of slides on that, but it's too short a time to show you that by changing it just by 0.1 millimeter, suddenly the ring just disappears. It's like magic like that. But you sit down there, 7.1, 7.2, 7.3, 7.4, and you can see the ring slowly disappear. And then when you go too big, the ring starts to appear again because you're mismatched again. Okay? So all these things are really exciting. I sit down there, my wife thinks I'm married to the computer. So here we are. See, you can see funny things start to appear. So you know that it's not right. So you can see this, you can see at the bottom all the various simulations. And then you can see this is not right. So you start to adjust the coma, adjust the stigmatism, adjust everything. And there's so many variables to adjust. Okay? Now, so I finally ended up with this. I ended up taking the spherical aberration away, which the shrink can do. No other laser can do individual removal. I got the pattern I wanted. Look at my treatment thing. I ended up with minus 4.38, minus 0.15, and axis 165. And then basically, this is what I got for the thing. Look at it. Looks very nice. As perfect as I could get. You know what I would have done now? This was when I started in the beginning. I would have made the optical zone a bit bigger. But we always try to do not too much corneal tissue removal because all these kinds of surgeries remove a lot more tissue than normal. Okay, because you're doing more things, you have to pay the piper. What I mean is that you have to give up something to get something. Okay, just like getting married. You give up your independence, but you get a companion all the time. So no choice. You give up something to get something. So you need to make a nicer zone, a nicer shape. You need to give up something. Okay, so this is the treatment pattern we did. And this is the treatment. It wasn't that long. I think it was like 50 seconds. And I chose transepithelial PRK. Why? Because the epithelium is uneven, which I showed you just now. Thicker over the scalp, thinner over the periphery. So this is what the final result looks like. Not bad, not bad. I wish I made it a little bit bigger. And this is the simulation on this side here. Not too bad. I think if I made the zone a bit bigger, it will look even better. There we are. Not too bad, I would say. Patient was elated. Higher order aberrations disappeared. No more glare, no more smearing of vision. Okay. Now, this lady came in and she's a normal case. She had this funny patch over here, and I went through the thing, look at the epithelium, look at this, look at that. And I did finally trans-PRK extra. Now, I know 99.9% of you don't believe in extra, and the talk showed all these ectasias. I haven't got an ectasia in the last, 15 to 20 years. I can't even remember the last time I had an ectasia. I'm treating other people's ectasia because I started doing LASIK extra long ago. And I have a patient who was minus 18, which I did, okay? So, and she's actually doing fabulous. She went through one pregnancy, no problems at all. So there are tons and tons of data on LASIK Extra. Go and look it up. PubMed, put in LASIK Extra or acceleration cross-linking. You'll find that tons of data. Okay, I need to rush or else I'll run out of time. So basically here we are, same thing. You look at all the things. You look at the epithelial thickness here at the bottom there. Okay, so here's the treatment. Very, very unusual because your centration is off to one side. Okay. And there's the simulation. So these are ideal for this kind of unusual cases. And then you can see funny ones that come up here, there, here, there. And this is my sort of algorithm. I do a full corneal wavefront, it comes out funny looking. I do a symmetrical or asymmetrical aberration free. I do aberration free coma. I do corneal wavefront, spherical aberration filter. So these are things I do on a routine basis. So this is the pre-op here, and that's the post-op. This is at 0.25 scale. This is the difference map. Pretty good. If you look at the difference map, you can see almost coming out exactly what is expected. So this is a smart complication, and you all have seen so many just now. I don't want to go through this, but this is, I basically recentered the patient. Then this is the print out. This is the smile that's decentered. And you can see, look at ablation, nothing here, a lot at here. Basically think like a laser. If you've got too much ablation here, you add ablation to the side here, and this is too flat, so you need to give a bigger ablation over there. And I find that trans PRK is slightly less accurate compared to LASIK or old PRK. The reason I think the biomechanics is slightly different. Okay, that's a hunch. I'm just looking at the cases. So that's the treatment. Laser more here, no laser where the lenticule extraction took place. Obviously, that's logical. You took it out with the lenticule. So the other parts you didn't take out, you have to take it out with the laser. Okay, then you can see all the simulations. It's a final result. I still don't like it because you see, it's still a little bit too much ablation here. So, you know, over here, you can see where the laser was doing something funny here. Okay, so it's not perfect. You have to sit down and you have to slowly look at different ways of treating. Now, at present, you have to look at each simulation individually. It's hard to remember essential details of each simulation. So I print out everything manually. It's tedious and slow. Only crazy people like me do this. You should see my bedroom. Sometimes there are 40 printouts lying on the floor, and I'm looking at them all. Then I collect together and say, this is rubbish, throw away. This is rubbish, throw away. This is good, this is good, this is rubbish. So I ended up with one pile of rubbish and one pile of good. Then from the good, I say, which one is the best? Then I go through one. So, you know, I waste a lot of paper. I kill a few forests probably. Okay? So I created a sort of like a nomogram for myself. I will do this first. I will usually do trans PRK because these are difficult cases. Then I will put down all these different K readings and this, and then all the different things. I can go into details, but we won't have time to do this. Then the next thing I do, that's step one. I put in all the things and I print out everything to look at them all. And then I start to look, step two, I change the ablation diameter. This seems to change a lot. So I change from 7, 7.5, 7.6, 7.4, 7.8, 8.0. And then I watch the patterns changing. Okay? Then after that, I look and I try to save some tissue. So what I do is I go to shrink. They have a special pyramid. You put in minimize depth, minimize volume, and then you see what happens again. So it's very, very tedious. Sometimes I take a case, I take 4 or 5 cases, for 4 or 5 days to do it. So I needed to validate it, whether it's correct or not. So I'm going to go through this part very, very fast. So basically, I took all the data because the shrink R&D people want to see data. So here the data, every little thing I put that on every eye for all the patients. And we plotted everything. And to our surprise, the estimated K reading and the actual K reading, that means I'm comparing actual patients had surgery compared to predicted K reading, I got a parallel line, almost lying on top of each other. Okay? The simulated one is on, wait, let me see. The predicted one is on top, simulated one's on top, and the real one is at the bottom. Almost straight lines and both parallel. Means the prediction is very good. Only thing we needed to do an offset. That means we needed to adjust the thing. This is the other eye, because we thought maybe right eye and left eye will be different, so we did right eye and left eye. Again, parallel lines, almost perfect, to our surprise. Because I expected the lines to be all like that sort of thing. Anyway, 88% of them were within 95% for the K readings of 0.88 diopters. Not very good. I expected it to be a bit better. There you see, this is the joker that killed me. There's one case that's like outlier of it. So difference in corneal toricity, 0.6 is 95%. At corneal thickness changes, 15 microns difference in 95%. 15 microns difference in 95 for ablation depth. Spherical equivalent, 0.75 with 95% of cases, not bad. I think this should be 0.25, okay? It should be 0.75. Cylinder, surprisingly, cylinder was really, really good. So post-op cylinder prediction was only 0.25 off. Okay? That's how good it was. Why? Because it told you whether it was coma or whether it was cylinder. So that helped a lot. Okay. Now, spherical equivalent is 0.75. Not that great. Oblique astigmatism. That was the one that tricked us a lot. Oblique astigmatism, but not too bad after all. Okay, so I'm finishing now. The real post-operative outcomes, 98% achieved 20/20. This is a real patient. Predictable refraction was within 98%, was in plus or minus 0.5. No